So this talk is not going to be about the 4 billion years of Earth history, with continental drift taking up at least 3.8 billion of it. It's about the last 1/1,000th, the last 4,000 years of recorded history where humans recognised that continental drift was actually occurring. So it's the documentation of continental drift. And we'll start off with this first picture, which is taken from Carey's 1956 paper. It shows the reconstruction of the continents. These lines are the shorelines of the continents. The actual fit is more or less on the joins of the continental shelves. But it was, and still is, the most accurate reconstruction of the Earth. The reason it was so important was that he had used a stereographic projection. In other words, he used a system of coordinates whereby any point, like here, would have about a 280 degree from north easting location, and then it would have not 90, but say about 80 odd degrees of curvature over the top, over the centre of projection, which was 0, back down to 90 again. That caused minimal deformation of the continents. Africa is smaller than it actually is relative to the other continents, and Australia is larger, being nearer the edges. But in any of the continental reconstruction lines, the accuracy of the points on each side of it are spot on. So he was way ahead of the game in terms of what was going to be needed to convince people of such a remarkable movement of the crust. And he did it from Hobart in 1956. He effectively had a blank jigsaw puzzle. You imagine a jigsaw puzzle with no picture on the top. That's what he had. And then he started to build a picture that would link continents and their geology across these boundaries. And he could, in particular, concentrated on this line at the southern side of the Tethys Ocean. So this was the part of this hemisphere. This is just the land hemisphere. This is the part that was oceanic at the time of the reconstruction, which was about 200 million years ago. So what I want to do is trace the history of that line and look at the features that he spotted. First thing, he put the edge of the Australian block between New Zealand and Tonga. He then had a shear zone across to the same boundary, which was displaced to the west by that amount. And he noticed that all the way along this zone, right through Europe and over to the States and out the other side of the Gulf of Mexico, there was still an offset, which was in that sense, that is the top side moving left relative to the bottom side. So that was called a left lateral shear. It was basically a roller bearing. And what it did, it caused the continents like India to rotate anti-clockwise. And so this is a little anti-clockwise rotation symbol. And there are others that he predicted, for example, Spain, and of course the blocks in the Gulf of Mexico. So he had a uniform geological feature that he could trace across these boundaries. And therefore convince people that what he said was correct. And in particular, I've taken out the Mediterranean area, and this is what he did. You've got to remember, this is 1956. There were no smart geological maps of the world around. He had to make this map himself, and what he noted was this black unit here, there, over there, and then over here. So he interpreted that this Corsica-Sardinia block had migrated from here to there. Likewise, Spain had opened about the Bay of Biscay as it rotated in an anti-clockwise direction. Inside this solid part of that block, I've put two more anticlinal, anti-clockwise arrow directions over the Tyrrhenian Sea between Corsica, Sardinia and Italy, and then between the toe of Italy and the Peloponnese of Greece. Now, I want you to just hold that area in your mind while I show you the next slide, and I'll get you to recall it in the one after. Most people have accepted, most geologists have accepted that Carey gave the accurate reconstruction in 1956, but they implied that Wegener, the German meteorologist, in 1915 had also made a similar reconstruction. Well, his was a sketch, as I'll show you later, and it didn't, sorry, stepped out of it. But in fact, when I went back and just Googled and asked the question, what are the oldest continental maps? This one came up, and it was made by Eratosthenes at the Library of Alexandria in Greek-occupied Egypt around about 220 BC. So that's over 2,000 years prior to what anybody has ever proposed before. And now I have to defend why I did that. Well, first of all, when you see a map like this, you know it's got quality. It's got towns and cities on it. It's got other geography like this representation of the Taurus Mountains of Turkey and the Himalayas, and it shows them as three layers of high mountains. So he was trying to show an accurate map. Now, this blue line represents the coast of Africa, which at the time was thought to still be above the equator. There's the equator there. And that shows on this map 400 years earlier by Anaximander. That's the ocean there, which was found in 590 BC when Necho, the pharaoh of Egypt, had just taken a big trouncing from the Persians in 609. So he got his mates in Phoenicia, who had also set up Carthage, and said, look, you're good navigational people, could you circumnavigate this place and see if in fact it is a separate continent? And that was done. It took 3 years, and on this map, 220 BC, Cern Island has been recorded. And this is all done on historic data, mainly collected by Strabo in 18 to 7 BCE, so 200 years after this. But that meant that that this was known. It was also known as a gold area, and Greece sourced gold from the Cern Island area, from onshore Africa. Now, in 310 BC, just prior to this, there's a sequence here. All these Greek scientists were working on top of one another, following each other. In 310 BC, Pytheas sailed from Marseille up, did a loop around England and went up to Thule, which we now know as Iceland. And there he observed that on the winter equinox, where the sun was not visible beyond that. From that he calculated that he was 23.5 degrees from the pole, and proposed that the tilt of the Earth's axis at that time. That's how early that was. And in 15 years later, Dicarchus noticed that you could draw a straight line from the Pillars of Hercules, or the Straits of Gibraltar, between Italy and Sicily, under the Peloponnese, over to Rhodes. And he called that the major parallel. He then drew a line perpendicular to that, which was a meridian, through Rhodes, down through Alexandria and Syene, and knowing the distance from Syene to Alexandria as being 5,000 stadia, which is divided by 6, and that's kilometres, about 800 kilometres. He realised that at the Tropic of Cancer on June the 21st, that the sun would be directly overhead. So if he was in Alexandria looking down a well or had a flagpole up or something, if the Earth was curved, it would cast a shadow to the north. If it didn't, then the Earth was flat. Well, it cast a shadow of 7.2 degrees, which is 1/50th of the of 360, and he got a circumference of the Earth of 250,000 stadia, which is so damn close to 40,000 kilometres that we have today that it's absolutely amazing. So, and that happened in 240 BC. Now you can see what he when it came to Eratosthenes, he decided that this right angle system of longitude and latitude, effectively, was a great way to make a base map. And so you can see these lines on here. You can see the other lines of the parallels, and then the meridians coming down like that. We would call that a Mercator projection, which incidentally was invented in 1569 CE. So there's a disparity here. This ought to be called the Eratosthenes projection. And he then did something that was particularly interesting. He noted that the 3 rows of mountains that he'd drawn there, and that these were very high and formed a particular zone. And he called that Sealstone number 1. They were using seals for trading and other legal transmission devices, and the stone, I suppose, is the rock. But what he was actually doing with a sealstone was creating subcontinents. Here, for example, is the subcontinent of India, the subcontinent of Arabia, and of the Mesopotamia, and here the Levant. Now, that was his sealstone 2. That was drawn diagrammatically from translations of Strabo by a New Zealand lad in 2011. That's how recent this is. This is fresh stuff. And he noted that he drew this diagram here. His name was Cameron McPhail, 2011, and he drew India as a slightly rhomboidal. He had better evidence for Ariana being rhomboidal, 14,000 stadia there, 13 there, and skewed over square, if you like, which he implied the Eratosthenes knew the concept of a roller bearing or a left lateral shear. And then in the third area, in this solid red area, Sealstone 3, he knew that Posidonius had plumbed the Tyrrhenian Sea and found it to be 12 stadia, in excess of 12 stadia deep. In other words, 2 kilometres deep. It's actually 4,000 metres deep today. And he figured that that was an extensional area, and that Italy had rotated anti-clockwise relative to Corsica and Sardinia. Likewise, a lot greater distance from the Peloponnese of Greece out of Italy. Now, of course, that's exactly what Carey said. And Carey also added the rotation of Spain, but of course these Eratosthenes didn't know that the Bay of Biscay existed in there. So he not only took advantage of the geography, he created his own geology over that Mediterranean area and deduced these rotations, which are exactly the same as Carey's Tethyan shear of 1956, 2,100 years earlier. Abraham Ortelius, or Ortel, he Latinised his name. He was actually a very commercial cartographer. This is his map of 1570, which I found on a disused calendar in Switzerland some years ago. I was rather pleased to get it, and I looked up the story behind it. And in 1569, Mercator had drawn a straight Mercator projection from that red line there, which is the Tropic of Cancer, down 23.5 degrees to the equator, another 23.5 to the Tropic of Capricorn, and he wrote that on there. And then he found that Mercator's projection didn't sell very well at all. The beauty of it was that in this zone here, the distance between any 2 points could be measured horizontally with a scale rule on a Mercator projection. But the real world actually came to a point at the North Pole. So he said, well, I need to be able to put some of that curvature into this, and what I'll do is I'll decrease these meridia and make this top one about 60% at the pole. So there'll still be big distortion up here, but it won't be so bad as to bring into question the statement that he was about to make, that Africa, West Africa, appeared to fit in here, but more importantly, Brazil fitted into the Gulf of Guinea. And he did that in 1596. He sat on his map, which was actually the world's first atlas in 1570, and he got to know Bishop Thorlaksson of Iceland, who had done a map of Iceland and knew all about the current active zones on the North Atlantic ridge. And it seems highly probable that he wasn't just making a simple statement when he said it appeared as though the Americas had been torn apart from Africa and Europe. Now, he took his two best fits, or the single fit actually, between Africa and South America, and was very happy with that. Less so, but still fairly impressive against North America. And that's where he made his statement. His projection wasn't good enough to get it right up here. He was right in putting the offshore UK into the lower part of Greenland, but what he didn't know was that Spain actually rotated back there and back into here. But he couldn't make his map lay on a flat table, which it should do. This part did, and the only way he could get this other piece to lay flat, he had to cut it, and he just cut it straight along this edge here, which you can see he was guided by the drainage that he had put on his map. That's the Indus Suture. That's the Persian Gulf, and that's the Euphrates River up there. But in doing so, he created this gap. Well, that's the same gap that Prof made in 1956 when he had to create the Tethys Ocean because he had the same problem. He couldn't make the southern hemisphere and the northern hemisphere fit together. So in other words, the accuracy of Ortelius's map was amazing. Now, well, this all fell on deaf ears. This was 1596. And you've got to remember that the Galileo and Kepler, they were still a decade or two away, 1609. And the botanists were the smarties. They came next in 1735 with Linnaeus. The geologists were rumbling around, but not doing too much at all. And they didn't really do anything smart until 1815, which was 220 years after Ortelius. So there really was no science to pick up the achievement this chap had made. But anyway, Smith was surveying for the canal system, and he knew he had to get the softest rocks and try and get the canals to run horizontally or thereabouts across the UK. And there's a book being written about this recently by Simon Winchester called The Map That Changed the World. And it certainly did. He totally mapped virtually all of the UK and Scotland and Wales as well. And but to me, the real beauty of it was the cross section that he made. This is the cross section from Wales to London. And I took field trips along this cross section by trying to mimic the structure of the North Sea by doing it onshore. You can't really do it offshore. So we did this field trip 45 times from 1983 to 2012. It was a 5 to 7 day trip, and we walked in the footsteps of William Smith. I mean, this is Geology 101 for sure. The point that I didn't realise at the time was that the real Geology 101 that I was getting from Carey in the late 60s was just light years ahead of it, just completely way past it. But what happened here was this is the coal measures. They gave that age of those coal measure rocks Carboniferous, coloured it grey. There was a limestone at the base of it, which they called early Carboniferous, one at the top, which they didn't have a name for, and then they were sandwiched between two red units, the red marl, which became the new red sandstone, and the old red sandstone, which the geologists recognise as the Devonian. Now what I've done here is take the Jurassic unit and I've coloured it blue, and we'll refer to this as the blue, the green for the chalk, and orange for the youngest unit, which is in the Thames Valley. So we don't have to get tangled up in any geological terms. And what I concentrated on was this area. We did the coals and that limestone, but we worked mainly across this boundary here, the Jurassic-Triassic boundary. Now, the first test of the use of this cross-section in terms of global spread was that it was obviously okay in the UK, and it was quite all right in Europe. In fact, the Jurassic age came from the Jura Mountains of Switzerland, and the Cretaceous came from the French chalk units of France. Now, shortly after, in 1831, Darwin started off on the voyage of the Beagle, and the first test he had of the Smith diagram was here in Hobart in 1836. But what he did, they left London, went down to South America, and it took 4 years to get from the top of South America round the bottom and up to the famous Galapagos Islands. But when he was right down near the bottom in Tierra del Fuego, he found that there was the remains of the main glacier ice cap over the Tierra Fuegan Andean zone, and that ice was flowing out as breaking off as icebergs in Kelly Haven in Tierra del Fuego. And he noticed that as the icebergs were floating past, that they had big chunks of rock in them, and that as the iceberg warmed up and heated, the rock would drop down into the mud below. So he called these drop stones. And he wrote back, and I suppose it took a few months to get there, he wrote back to the geologist of the day in London, Lyell, Charles Lyell, told him about this new form of sedimentation. Because at that time, they were only just really realising that water flowed downhill and it dropped the sand off first, then the silt, and then the mud. And here was a way of getting big rocks out into fine stuff. Well, it completely misinterpreted the fact that these things, it was gravity that dropped the drop stone into the mud, not the horizontal motion of the water. But the churchmen of the day, of course, took this up as a new mode of deposition and accounted for all the tillites and all the glacially derived material all over Europe as being derived from the flood. Right? Well, that becomes a problem, because when he got to Hobart, he arrived on a Friday night and spent the next day walking around Hobart and going out to Cornelian Bay. You know, those boat sheds on the bottom side? Well, behind that, he spotted that there was a old beach deposit. And he noted that sea level had always remained constant. That's what he'd been told by Lyell. So therefore he assumed that the land had risen about 2 metres. But it hadn't. sea level had dropped 2 metres over the last 7,000 years, and that was the same drop that Eratosthenes had seen in the Mediterranean. So it was he didn't get that right, and his concept about sea level was not right. But he took a little ferry, which was really a steam-powered dinghy, about 6 people on board, and on Monday morning, on the 8th of February, he went across to Bellerive Pier. It wasn't a pier at the time; it was the slaughterhouse for the meat supply, the kangaroos, for Hobart. But anyway, he walked around the Kangaroo Bluff, and he saw things like this. Here, this is mudstone, but here, in the middle of it, is a piece of granite. That's just over 3 centimetres, so it's not very big. So about that sort of size. But that had dropped down, and he knew that. You could see these beds were actually dipping down into it where the thing had dropped, and then the mud had then come back horizontally over the top. So he actually wrote in his field notes that this reminded him of what he'd seen at Killy Haven. But he also found a collection of fossils, mostly this type, Spiriferids, in amongst these mudstones and sandstones above it, and also a few more down at Port Hill Sands Bay. And the trick was, well, could these give him a William Smith age for this material? And the answer was yes, it could. When you Google Smith's collections, you find that he had fossil collections for many of these units, particularly the marine limestone units. And one follower of his work was a fellow easy to remember, John Henry Pepper. He made this photograph of the fossils that he saw in that limestone unit in northern England, and so he deduced that straight from the diagram that had to be either the late Carboniferous or the early Carboniferous. Well, these are all coralline tropical things, just like the tropical coal deposits, whereas over here is the Hobart collection, and these corals are all very different. They're much smaller, they're colder water, very cold. In fact, they're sitting below the ice shelf. And but again, a pretty similar looking Spiriferid. So the best you could do is say, well, this is the same as that. Therefore, the drop stones in Hobart are also early Carboniferous, possibly late Carboniferous. Spot on. However, Max Banks, Max Banks Medal, of course, for the Royal Society here. He was my lecturer in stratigraphy and fossils, and in volume 105 of the Royal Society, he published part of Darwin's field notebooks, which he had picked up from the curator of the Darwin collection in Cambridge. Now, Julie and I were in London at the time, in about 1977 maybe, and Max and Doris and the 5 kids came over for his sabbatical leave. He bought an old ambulance and got the wife and the 5 kids and me. He's driving around it was a lot of fun. Anyway, the point was that in 2009, he created this little booklet, which is this one, and it has the 18 pages of Darwin's field notes in it, plus the commentary by he and David Lehman and others, and it's great value. Now the thing is, in 2019, my mate Ross Large said, "Oh John," he said, "see these dinosaurs over here?" Ross organised a Royal Society dinosaur exhibition. And he had his son in the first one. You can see the zipper mark there. Oh, you've done it up. And it was a great show, but he came up and put his hand on my shoulder and said, "Oh, guess what?" I go, "Oh no, what's going to happen now?" He said, "Would you like to give a talk about Darwin in Hobart as just as part of the filling for the dinosaur show?" Well, I had partly misunderstood what Max was on about. Max, I thought, was aware of the Voyage of the Beagle notes, and that he actually had the detail in this book, but it wasn't true. The notes in the Voyage of the Beagle didn't include the drop stones, it just included the age. Well, in a four-dimensional world of 3Ds of a rock and its birthday, he only had one dimension of what was a four-dimensional feature. So the question is, why did he do that? Why did he not publish that he published that he'd seen these Carboniferous fossils, but he didn't say what the environment of deposition was, either in the first version of the Voyage of the Beagle or the former one in 1845. And this concerned me, because I was trying to backdate things back to Eratosthenes, trying to get the timeline more filled in, and there was Darwin squirreling away one half of the evidence, and we know that he it wasn't an accident, because I then looked it up. I looked up the history of John Dalton Hooker, the famous botanist, who also did a lot of work out of Tasmania. Twice he was here for 3 months at a time. And he was on the Ross expedition effectively straight after this, down to the Ross Ice Shelf in 1839-43. And he and Darwin had an argument, a formal gentleman's argument, in writing over the validity of the drop stones. And basically, Hooker took the view that his work on the botany of Australia and South America required a land bridge, namely Antarctica, to allow the transfer of the species across. And Darwin agreed. He said yes. He said that concept is okay for the specific example of the Galapagos Island. And that is, you've got 4 or 5 islands that Darwin visited. He found a different tortoise on each one and a different vegetation on each one. But he was worried about creation and starting another evolutionary argument in 19th century England on top of what was going to be his ace when he got home, which of course was the origin of plants and animals. And so he left these out. And my comment is, this was actually the first proven continental drift since 1596 in 1836 in Hobart. In other words, we was robbed. So it, I don't think it's so funny. I find it very irksome. Anyway. So, but this had a marked effect. You see that the first botanist to do any serious work in Tasmania was from Bruni D'Entrecasteaux's expedition, Lavadelier or Lavadelier, something like that. And he found, he did make quite a study of the modern plants, but he may have found the first fossil of Glossopteris browniana, which was actually found in the Newcastle coal measures in about 1805, and the first French paleobotanist working on fossil leaves was Brongniart, Adolphe Theodore Brongniart, in 1828, and he named this fossil Glossopteris, he named it Browniana after the botanist who gave it to him had been on the Flinders expedition, the next one after D'Entrecasteaux. So Muggins here thought, that means there could be a Glossopteris before that, which was from the original French one. Well, I've been chasing that down for the last 2 months, and I've come up short. But I have found that fossil in the Mount La Perouse rocks, which is where I did my honours in '69. But that's another story. But it is very significant because there was quite a break between 1596 now and 1858, when another chap who lived in France, it doesn't look like a very French name to me, he keep going. All right. He made a sketch map, and this was the problem in the 19th century. Made a sketch map of the Americas against Africa, got the tail on South America correct, and notice he put in Australia. This. So he was taking Australia, which was way on the other side of his globe, and putting it in against Somalia. This looked like the French botanist and the French geologist had been reading the same papers, each other's, and he put Australia in there. Now, that was the first example of any continent being restored in the Indian Ocean. This was the easy one, but this was the hard one. Now, another French connection down on the Isle of Reunion, which relative to Madagascar would be about here, Mauritius just above it. This was Roberto Mantovani, the violinist, not the American one, who was working there, and he noted that the data from Antarctica only showed 4 non-iced areas where you could see the rocks, and he thought it was split in 2. And he thought that this part here, which in fact was pretty right, was Wilkes Land, and that fitted into southern Australia. That's his first X. His second X, which is this one, he just popped in there. But his concept was that this was a radial movement of those continents away from Antarctica from that original position. Now, that was, I've had this sitting there so that you could look down the Atlantic Ocean indicating that continents are moving from west to east or vice versa. But when I was at the Exxon course in 1970 in Houston, I was shown the same thing, only on a bigger globe. And I said, oh, that's just not right. So turned up through 90 degrees. Now everything's moving north away from Antarctica. All right, we'll come back to that. I'll let you have a look at it. These are my belts that I've used to find my way around the Props Globe. But anyway, in 1912, 3 years after Mantovani made this reconstruction, this Glossopteris indica, which is the Indian version of the Australian one, the same species, cropped up with Captain Scott's body on the Beardmore Glacier on the Ross Ice Shelf. So this was the first time we had a connection between Glossopteris in Australia and Tasmania, of course, with Antarctica. We had it with India, but not with Antarctica. But there it was in 1912. The interesting thing is that the so-called father of continental drift in any American paper is Alfred Wegener, but it was 1915. So it was after Mantovani's reconstruction, which had a logic to it, after the discovery of the key fossil Glossopteris, and after his sketch map of the world. Yeah, the big problem was, when you compare that with this one, Prof was left with a gap, the Tethyan Ocean. The only sign. Well, yeah.
We've got some problems, John.
The only sign of a little Tethyan Ocean on the Wegener map was a little gap off northwest Australia, and that was meant to be there pre-blue, pre-Jurassic. Well, I know that wasn't right because I drilled 2 wells in over a mile of water out on Exmouth Plateau, and the sands were still coming from the north. So therefore the sketch wasn't right at all because it didn't have the Tethyan Ocean. So long and short of it was that Prof's map was vastly superior to Wegener's. So there we are. I've just drilled 2 great exploration wells, both with gas in them. But Esso was looking for oil on Exmouth Plateau, not gas. And so I thought, well, I better just get out of here. Because Prof had told me in 1970, he said, by all means join Esso, my boy. He said, they're the biggest oil company. He said, you'll learn everything that you can learn from them in 10 years. He said, then go and hang by your own tail. So I said, all right, so I'll be a consultant. Well, so I came back here and we did all the work that related to the discovery in Bass Basin. But then in 1986, I decided to take a closer look at my situation. I took 10 billion barrels of oil, a fair quantity of oil, but not a lot. And I just made that my scale, and then I took the known produced and reserves of each country in the oil and gas encyclopedia, so the numbers were probably pretty right. And this is the map I got. where's the oil in the southern hemisphere? What a place to be a consultant. So it was pretty obvious that, and Kerry's map actually was telling us this too, because that equator there, the boundary between oil and basically gas, that is a marine algal seaweed-like source for oil versus a coaly gaseous source, woody source for gas, was in fact this line here, which is damn near that one. And so I should have realised earlier that things were going to be drier and more non-marine in the southern part of the southern hemisphere than in the tropics. So we packed up, and oil went to $7.50 a barrel. We packed up and went to Dubai with the 4 kids, and had a great year there. And then I was developing work in the North Sea, both on the UK side and the Norwegian side. And that's the only reason we stayed alive. The interesting point that comes out of this is that this is the blue oceanic crust. That runs from 145 to 200 million years ago. The green stuff is the Cretaceous, which is from 145 to 66, and then the orange is the younger stuff from 66 to 0 at the ridge. Now I'm reminded of Keith Corbett's talk here two months ago, when he talked about his boiling billy theory for continental drift. And in fact, he's spot on, because these continents all rotated apart. All motion on a sphere has to be about a pole of rotation. Eventually these poles turn into hotspots, and these hotspots are generally trilete. Now if you look down on Keith's billy, you won't see those 3 lines, because it's boiling too hard. It's turning the whole show over, but it's boiling too hard. But if you look down the throat of the Kilauea volcano, and there's some excellent photos of it, you see exactly this, that each one of these is a round plume, but they join up, and you see that they are equally distributed around the southern hemisphere, but not up here. Prof always emphasised the asymmetry of the Earth, and it is absolutely fundamental. And so we're going to have to take that apart a bit. The reason that we know more about the shape of these things and their geometry is because I remember it well, in October 1957, the Hobart Mercury published a picture of the first data that came back from the Sputnik 1 satellite, and it showed that there was a slight high in the top of the Earth. There was a normal bulge, of course, due to the rotation. That was 21 kilometres. There was a little bit of a depression in the southern hemisphere, and there was a bulge in the southern hemisphere as opposed to a depression in the northern hemisphere. So the Earth is not a perfect ovate spheroid. And now you can say, well, that's not very much. That's, if I made that 6.5 metres, and the radius is nearly 6,500 metres, that's only 1 in a million. But it's enough to make the difference. So let's take a look at that. Here's the Earth as a composite with that geoid on. The geoid is a name that was it wasn't actually coined by, but was obviously understood by Archimedes. He invented the idea of the principle of flotation, like ships, right? And therefore, he said that all stellar bodies, planets, would have to be spherical, because the weight of the rock from any point on the surface to the centre has to be the same all over. It can't be a box, because the corners would get crushed, because they'd be much heavier. So these anomalies are significant. But of course, with plate tectonics, that's not their concern. They came off Prof's New Global Tectonics of 1956, and they called it plate tectonics. That they had to be a little bit different. And the idea was that there was extension between South America and Australia. You could see that by the new oceanic crust in between. But also, on their simple model, what comes up must go down. So down the edges of the Pacific there and down this edge here, they had to subduct it. Well, isn't it strange that the fastest last 66 million years to recent, just almost twice as much of what it was trying to bury, was also being created in the Pacific Ocean. So their model is way out. It's also asymmetric, because down the bottom you've got these nodes, these 4 nodes. You'll see young crust around it, then the green crust, and then a little bit of blue, then Antarctica. There's no subduction around Antarctica. So their model only applies to, well, from the P to about there. It's the top part of the Earth. You know, that's the part that the Northern Hemisphere people and particularly the Americans see. So that's all they don't know about the South, because it's not like that. It's going from south to north. So therefore, there has to be an explanation, and you better fasten your seatbelts. I started collecting data from the first satellite, first GPS data. From 1978 to 1988, they set up some 23 stations on the Earth and worked out the rate of change of the radius of the Earth. And they had it increasing at 4.15 centimetres a year. Now Prof in 1956, he required 16, so he was well over. But we didn't know that in 1993. In 1993, Prof got an invitation from the astrophysicists asking him to come and talk at a astrophysics convention in Olympia in Greece. And I owed him a lot, so I said, I'll take you, Prof. And we went. And I was glad I was so generous, because I met the second really smart person in no time, and that was Houghton Arp. Houghton Arp was fired by an unsigned letter from the Mount Palomar Observatory for taking pictures of naughty galaxies. A naughty galaxy was one that wasn't all the same redshift. See, the Big Bang theory requires that the recessional velocity is expressed by the redshift of the X-rays, and and therefore they get brighter and brighter red, and then you can't see any more because you've gone beyond the edge of it. And that's how they calculate the age of the Earth. Well, how do you do that when this is a mid-red galaxy? It's got a bright red quasar there, and this probably is too, and that light blue that you can barely see is even a blue redshift, which is lower again. So they all live together. And in fact, the nearest galaxies to the Earth are quantized. They're in steps of 37.5 kilometres. So we've got two problems. Our two big theories, the Big Bang and plate tectonics, are at the very least grossly deficient. So he gave the principal address and gave these many examples of these. He had volumes of them. And I looked at it at the Milky Way galaxy, and I found that the Earth and the Sun is 25,000 light years from the centre of the galaxy. Now, a light year is actually 1 trillion kilometres, give or take. So 25,000 trillion kilometres, I mean, it's unbelievable. What is almost unbelievable is the fact that on the arm of the spiral that we're on, it's nearly 1,000 light years thick, and the Earth is actually 56 light years above the centre point. So could it be that there's extra mass below the southern part of the Earth, giving it that little pull and giving it a nudge? And is that in some way related to expansion? Now, Harp came to my secondary talk, and he said to me after, he said, if you're right that the Earth is expanding, and I was still a big expander in those days, prof scale, 50% increase, he said the Earth's radius will be increasing at less than 10%, and it will be pulsed. Now that really rang home to me, because I had started to take these courses in Smith's type section to show the details of the minute structure that they might see out in the North Sea on seismic. And this is one little section on the Somerset coast, and you can see this fault going down through there. This unit here thickens towards the fault, so therefore it's going down on this side. This one is too. But look at this one, it thins. Then it goes back to thickening again. So you've had general slow extension and then a push. And the next one up is this feature. This is in boring intermittent limestones and shales. And this has been folded, then cut by an extensional normal fault, and then normal deposition starts again after it. It's another one of these little compressional pulses. So the question is, were these the pulses that could be related to expansion that Hart was allowing me to have? Now, here's those two pictures again, and here's the same seismic line. This is the interpretation done by Shell, and that's the well. And these faults here are all extensional. So it's been pulled apart, and the basin goes down. Very simple model, but in fact, if you look at it, if you take a look at this data here, I wouldn't put that fault there, I'd put it there, like that. And then these are folds, and this has been pushed at these times. And there's the folding occurring at the late Triassic, and there it is, the early Jurassic. And what I haven't done is look at that truncation and then the onlap on top to see where the 180 million year one is, because that's the age of the dolerite in Tasmania. So that's work in progress. But in any event, that's how I would interpret that seismic line. And would you know it? I took a party of 6 blokes from Shell, managers and juniors, on a trip, and we looked at this outcrop, and we looked at that section, and the fellow who interpreted the seismic and had the well drilled, he was there. And after he'd heard my story, he still put his hand up and admitted to drilling the well. But, well, the answer was pretty simple. Was after the course, the boss man asked me up to Brunei for a few weeks with Shell. So these things then appear like this. That's 350 million years down there on the bottom. You can't read that. I can hardly read it myself. But there's 30 of these compressional events, and I've seen them in most continents, north, south, east and west, in over 19 basins, and they're always laying on these specific zones. And these are the two. They're quite prominent throughout the late Triassic and the late Jurassic, the new red sandstone and the blue unit. And here's where it plots on Pete Vale's eustatic cycle chart, sea level chart actually, for the world. And Pete was my boss at SO's lab time. All right, I'm nearly there. In fact, this is the last one.
Oh, there you go.
There you go. So I knew this chart very well. I knew the amount of work that went in, thousands of man hours, and it was very accurately done. It was immediately accepted around the world in academic institutions and the like, and except in Shell, because we were working together in the North Sea. But what happened was, I couldn't work out whether there was any real pattern to that. But it turns out that in 1912, the International Stratigraphic Group got together and decided the unit in here was too thin, and they thickened it up, and that this was too thick, and they thinned it down. And then you get this distribution here, and I had a mathematician do an analysis of it, and he asked to do it, and he found that my compressional pulses give the Earth a pulse rate of 13 million years. So there you go, you operate on about 2 pulses a second, and the Earth has one every 13 million years. So and he found another real good correlation at 3940, which is 3 times that. So I wanted Prof to read this, but it was very hard to talk to Prof. We used to go to lunch every month for 17 years, from 83 to 99. Had a great time, really great time. And so I put it between his 1938 DSC thesis that I just read and the shoebox of all his slides that June Pongratz had made for him over the years. And I put it in there, and at 11 o'clock on Friday night, the phone rang. "Prof here, my boy." "Oh, right." He said, "You've left your paper." He said, "I took the liberty of reading it." He said, "You still write very poorly." but he said, "You could not have 30 of those in 19 basins at 600 all occurring by chance." So he said, "It's worth a DSC." So he said, we'd only had lunch on Wednesday, that's when he got the paper. He said, next lunch, he said, "We'll get you a DSC." And I said, "Oh, all right, that'd be nice." And he said, I'll put the OK on it. And then, of course, we had lunch, And then 2 years passed, he died, and 22 years have passed, and I'm still here as John Davidson. However, because it has a pulse rate, any doctor will tell you that's pretty handy information. And you can actually work out stresses from this. And this is from the Valhall chalk field in Norway. And I could work out the stresses because of the pulsing at each level. And I could geosteer these wells and drill long horizontal sections of up to 2 kilometres long to produce much more oil. And they drilled 4 dry holes in 2003, and I put the next 2 down, and they were very successful wells. And it's just because rocks have a birthday. You know, they're like us. They're a three-dimensional thing, and they have an age, and that age is crucial. Thanks very much.
Yeah.
Great talk, John. Have we got any questions?
Considering the shape of the Earth that you drew and the theory about where it is in the rotational cycle of the Milky Way, is there any information on the other planets as to whether they have anything, a difference in shape that might be due to where they position in the plane of the Milky Way?
Well, I don't know.
Right.
But they'd have to have a Sputnik satellite to at least pick it up. Of course, now it's very well known. But it was picked up on the first satellite in 1957. So I would expect it.
Yes.
You said earlier on about what we now call countries, India, I think it was Brazil or Spain it was, that rotated anti-clockwise.
Yes.
So do they all rotate anti-clockwise, or is that just a convenient for the fit it into your talk? And if so, why are they consistent? Why do they go that way and obviously not the other way?
Yeah, okay. The question is, along that Tethyan shear zone, I showed those anti-clockwise rotating circles. That was because of the shear. If I move my hand to left hand towards me, that rotates anti-clockwise. So all objects caught between that shear will be like the shears in a bearing. They'll all rotate that way. Now, when I put, these are my belts, old belts that I put on. When I put the Tethyan shear zone on it, they look like they're all offset the same because of the big offset between Tonga and East Asia, and then this offset between North and South America. So it's all the one, it's just a question of degree. But I don't think that's the case for the opposite shear that takes India north. Well, in fact, it's this one. This shear sits at the bottom of the Atlantic Ocean, and this is effectively it's got a shear component to the extension, and the direction of rotation may change on.
Any other questions? Yes.
Going back to the beginning, you showed us that map drawn up by Eratosthenes.
Eratosthenes, yes.
Yeah. And you said that indicated that he had a knowledge that there'd been shearing between continental plates along that parallel, the road parallel.
Yes. Yes.
So, that seems extraordinary that he could understand that, with his limited geographic knowledge at that time. Is that a well understood theory that that's what he was saying, or is that speculation? Or
No, it's written up by Cameron McPhail, and it was. You got to remember that these fellows were working in sequence. They were all working together. These ancient Greeks, not like us today, and Dicarchus was the one who named that section of that shear the diaphragma, and that name was used by Eratosthenes. So he took it from the observation that it was a straight line anyway, and then he took the distance of in stadia of the separation from Italy and from Corsica, and from Italy from Peloponnese. And it's a couple of thousand kilometres. So the top side of it has rolled towards me relative to the lagging. And the reason is that as the continents move north, there's more rotational inertia in the north, going into the northern hemisphere than the southern hemisphere. So therefore the northern hemisphere tends to lag. The ships are bigger.
Yes.
In the conference that you and Prof went to, was it Art the speaker?
He was the.
Okay. You were saying that our solar system is above the plane of.
Yeah.
Is the Earth or the solar system going up and down around that plane, or is it always staying above?
Yeah, that's not a bad question. Did everybody hear that? Well, yes, we hear about things moving in and out of the galactic plane, and in fact the astrophysicists love that 13 million years because that's the number they've got for the Earth going in and out of the galactic plane. So I'll say yes to that. Thanks very much.
We'll close it off there, John. Thanks for giving this very interesting talk. It's appropriate that it's given in this lecture theatre where Carey gave many of his lectures, and it gives us an insight into the thinking of how the continents fitted together going right back to the Greeks, and seeing how that progressed through to Carey's day, even though Prof didn't know about that previous work.
We did.
The fact that he came up with some similar reconstructions, although far more advanced, is amazing. So thanks for bringing that to light.
Good.